Cool. Can everybody hear me okay? Sweet. Today is not the last lecture. We still have two more after this, but this is the last week. So we're in kind of the final stretch here. And today's gonna be a pretty cool lecture. So we're just gonna be talking about a case study in health, and it's gonna kind of combine almost everything that we've learned so far in the class. So, we'll try to make it pretty interactive and yeah, it'll be cool. It'll be almost like a mini review of what we've learned so far. Cool, so a few announcements. Homework 12 is due Friday, last homework of class. Project 3 is due Friday. And there's a couple project parties that have been set up tomorrow and Wednesday. So please check those out. There's a Piazza post here that you can click on in the slide notes to get to that. And as some people are mentioning, please fill out the course evaluations and the final feedback form. So if more than 80% of the class fills that out, everybody gets 2 bonus points on the final. So it's a freebie. So just make sure everybody in the class does this. Make sure everybody, yeah. If you know somebody who hasn't done it yet, just get them on it. Cool, and then there was one other thing I believe. Oh yeah, final conflict form. So we have a set exam time, but if you have some legitimate conflict with that time, please fill out this form by Monday, and then we'll try to see if we can make some accommodations. So that's kind of the last announcement for today. Is the final feedback form different from the course evaluation? Yeah, it is. The final feedback form is more for us that we've created to get feedback on the course, and then the course evaluation is more like an official thing from Berkeley that you're supposed to fill out. That goes into official records for evaluation for the course and the instructors and everything. So please make sure to do both of those. Those are different things. You should have gotten an email, potentially from the College of Engineering, about the course evaluations. Or I think you and I shared a link further up in the chat. It's course-evaluations.berkeley.edu. So either of those should work. Cool. So before we get into the case study, I wanted to really quickly just review some of the stuff we did last time. And I won't spend too much time on it. But basically last time we went over this concept of updating your predictions. And the idea was that you can have this concept of subjective probabilities and just priors essentially. So you have prior beliefs about something. And then once you get additional information, it changes kind of what you think about the probability of some event happening. And so we saw this in the context of some disease. And this was a Harvard study. So basically they asked a bunch of Harvard medical students to try to answer this question. Basically there's some super rare disease. It's 1 in 1,000 chance of somebody getting it. And then there's a test that's been designed to detect whether you have the disease. And then that test has a false positive rate of 5%. So what that means is even if you don't have the disease, there's still a 5% chance that you're gonna come out positive on the test. So the test is basically a little bit conservative. You can think of it like that. It's gonna say people who don't have the disease are still positive. So that's possible still. So that's kind of the main thing that we know, main information that we know. And so to answer the question, basically the question was, if you come out positive, so it's kind of the reverse. So it's if you come out positive on the test, what's the probability that you actually have the disease? So it's kind of flipping the question over. And so, to answer that question, we talked about how we can use a tree diagram to do this. And so if we use all the information that was given in kind of the problem statement, this is how we could fill out our tree diagram. So disease has 1 in 1,000 chance occurring in the population, and then 0.999 is the chance of not having a disease. And we know that if you don't have the disease, there's still a 5% chance of testing positive. So this is called a false positive. And then the information that we didn't have was about what's the chance of testing positive or negative if you do have the disease. So this wasn't given in the question. And we basically just assumed that these numbers are 1 and 0. So we basically just assumed this test is gonna be perfect if you do have a disease. So if you do have the disease, you're for sure gonna come out positive. And then basically now we have our entire tree diagram filled out. So then the question was, okay, if I know that you tested positive, what's the chance that you actually have the disease? And so we talked about how when you model out or write out all the different ways that things can happen in a tree diagram like this, then calculating probabilities of events becomes a little bit more straightforward. And so the basic idea is the probability along any sequence of branches or any path you could say is just multiplying all the probabilities along that branch. So for example, if I wanted to know what's the probability that I have the disease and I test negative, that's just probability of disease times probability of testing negative given that I have the disease. So that's going to be 0.001 times 0, that's 0. So basically there's no chance that you can have the disease and you test negative. All right, so what's the probability that I don't have the disease and I test negative? What's the probability of that? Well, that's just going to be 0.999 times 0.95. So basically, if you want like all the events along a branch and you want to know the probability of having all those things happen together, just multiply through the path, through all the branches in the path. So that's basically what we did there. And so the idea is if we wanted to know that you tested positive, we know that we're going to be in one of these two pathways. So either you're going to go to no disease and then test positive, or you're going to be having a disease and you test positive. So we can basically ignore the other two paths, the other two branches in this case. And so we just need to worry about these two pathways to get to testing positive. And then the idea is we're trying to answer the question, if I've tested positive, so I know I'm along one of these paths, what's the probability that I have disease? So basically, if I know I'm along one of these two paths, what's the probability that I came along the top path? Because that's the path where I have the disease. That's basically what we're trying to answer the question. And so how do we answer that question? Well, actually what we can do is just take the probability of going along the top path, the one that we care about, and then divide it by the probability of going along either path. And that basically gives us the answer. And so that's how we can do this. So essentially, you're trying to answer the question, what's the probability I have the disease even I tested positive? So that's just probability along the path that we care about, which is having the disease and testing positive. So that's 1 in 1,000 times 1. And we just divide that by the probability of going through either branch. And so either branch means that you can sum up the probabilities along each branch. So you'd have basically the probability of the first branch, that's this thing, plus the probability of going along the second branch. And so this is how we can basically answer that question. And so it turns out when you do the math for this, you get something like 2%, which is like super low. So it means that even if you test positive, chance of having disease is actually very low. Why is that? It's because the number of people in the population who have the disease to begin with is like super, super small. 1 in 1,000 basically. So like very few people are going to be in the population who actually have it. Whereas you have a lot of people in the population who don't have it. And so even though you have a lot of people in the population who don't have it, and only like 5% of that population is going to test positive, that 5% of a really large number is really, really large still. So basically, think of it like 5% of a really large number is still really big, whereas 100% of a really tiny number, that's still really small. And so that's why basically out of everybody who's testing positive, you're still going to have a lot of people that don't have the disease. And so we kind of went through showing that intuitively in like a table. And so I encourage you to go back to the last lecture to look at that if you kind of want the kind of visual proof of like why that's the case. I think that helps like really explain it well. So this is basically how we can kind of think about writing out and like calculating like a sequence of steps of events that can happen where there's like dependencies. So like, testing positive or testing negative actually depends on whether you have the disease or not. The rates are different. And so this is how you can kind of write out that dependency, and then that's how you can make the calculations. And so the idea was, this is the probability of having disease if you test positive, but this is also in the context of like just anybody in the population. So if you take any random person in the population, test them, they come out positive, then the probability of them having disease is just 2%. So it seems like it's a useless test, but the idea is when you do end up taking a test in reality, typically there's a reason for that. Like either you think you have it, your doctor thinks you have it. And so you should be able to model that as well and think about that mathematically too. And so we can do that using subjective probabilities. And so if you remember the information here, this is called the prior. So this is like, before we see your test, this is what we think your chance of having disease is. And then the idea is you can update that prior if you have additional information about that patient before you take the test. And so that's how we can do this. So this is the concept of subjective probabilities. And so basically the idea is up until kind of this last lecture, we only talked about probabilities as like the frequency of something happening if you do it like many, many times forever, like, coin flips or things like that. But in this kind of context, there can be cases where like that's not possible. Like you're not going to be able to repeat the same exact thing under the exact same conditions forever, such as somebody having disease. That's just like one person, they have their one life. You can't just have like a bunch of parallel universes where you can like see what happens again and again. So we can't really like think of this problem the same way. And so this is where you can kind of bring in your own subjective degree of belief of something happening. And so again, we'd use this when like the frequentist approach maybe doesn't totally apply. and there's a reason to kind of try to quantify still the probability of some event happening. And so in this case, you might have your own belief about, whether you have the disease. Your doctor might have another belief based on like all the patients they've ever seen in their life, and your subjective beliefs are probably going to be different. So you're going to have probably different probabilities of the event happening, and that's just the nature of subjective probabilities. But the idea is like, can you come up with results that are kind of like reasonable and make sense? And so if let's say you went to doctor's office, they do like, and you think you have some disease, you're showing some symptoms or something, right? And so maybe the doctor thinks that, oh, okay, actually, you're not just 1 in 1,000 chance. I actually think you have a 10% chance now of having this disease just because of the symptoms you're showing me. So you still haven't taken the test yet. There's no information from the test, but there's information from your symptoms. So my prior is going to be a little bit different now. And so all we do is we take that tree diagram. Most of it looks the same, actually, if you think about it, right? So like all of these branches here are the same. The probability of testing positive or negative, whether you have disease or not, that's still the same. But what's different is the prior. So what we believe beforehand about your chance of having disease, that's changed a little bit. And so now it's like 0.1 maybe, because the doctor feels a little bit more confident that you might have it. And how do we, again, do the calculation of what's the probability of disease given that you tested positive? It's going to be the same exact math. So we kind of cut out the negative branches, and then we just take the probability of going along the branch we care about, which is disease and testing positive, and divide by probability of each branch. And so if you look at the math here, it looks almost identical, except we've replaced this 1 in 1,000 with 0.1 now. So that's gone up. And then the 0.999 that was here, that's gone down to just 0.9. So that's the only difference in the math here. But that difference is pretty substantial because now the probability goes up to about 69% compared to what it was before, just 2%. So basically the idea is that, the doctor already had like a pretty strong belief going in that you might have the disease. And so that's why now the probability that they think you have the disease given the test is also higher as well. And then lastly, let's say that in addition to the symptoms, the doctor does like a physical examination and like, does a bunch of other things like while they're with you in the room. And now they see some additional signals that's making them think you probably have the disease. And so now that prior maybe now goes up to 0.5. So it's like even higher now. So we can try the same math again, just replace the 0.1 with a 0.5. And that means the 0.9 here also now becomes 0.5 because these two numbers need to add up to 1 basically. And so then if you do this math, then you get 95%. So now the chance of you having disease suddenly has gone much higher, at least in the eyes of the doctor. And so this is kind of how you can model the subjective probabilities. Cool. So any questions on any of like the tree diagram stuff or like updating probabilities, subjective probabilities? Okay, cool. So let's get to the case study. So this case study is actually inspired by a podcast by Malcolm Gladwell. So I'll share some information on like if you guys want to listen to it. It's really, really cool. And basically it's about revisionist history, like going back and interpreting things like differently, or maybe just like, maybe with additional information or maybe with the same information, but just like additional context or like a different lens. So really, really cool. And so the episode we're going to be referencing for today is season 2, episode 10. So I encourage you to listen to all of it. It's a pretty cool episode. And so the subject of this case study is going to be cardiovascular disease. So basically talking about like heart health. And so there's this specific disease like atherosclerosis. I'm not sure if I said that right. And basically it narrows your arteries due to plaque buildup. So like over your life, plaque builds up and your arteries get like essentially smaller and smaller or narrower. And then that can cause all kinds of problems. And so this is the #1 cause of death and disability in the developed world. So it's a pretty important problem. Even in like really rich countries, people suffer from this. And in general, cardiovascular disease is like global cause of death. So very important problem. And what's interesting is we don't truly know the causes, but there are a lot of associations. So there's like tons of things that are associated or correlated with cardiovascular disease, like high blood pressure, diabetes, like smoking, obesity, so on, so on. So there's like a lot of things that could be kind of associated with this, but we don't really know what the cause is. So if we wanted to know what the cause is, how would we do that? Like, how would we understand what causes cardiovascular disease? How could we possibly try to answer that question? yeah, randomized control trial, randomized control experiment, basically, right? So that's kind of what we'd want to do. And so what we're going to try to do today is like focus on one of these variables. So I mean, any one of these variables could be causing cardiovascular disease, but we're going to focus on just one, which is going to be diet. And so there's been a lot of research on diet. Like a lot of deaths worldwide have been attributed to just like low consumption of fruits and vegetables by the WHO. And there's all kinds of like interesting associations with diet and like some of these other things that are associated with the heart disease. So like high intake of salt, that's linked to blood pressure, high blood pressure. And that high blood pressure is linked to the like heart disease. High intake of like processed food leads to obesity, and obesity is associated with heart disease. So there's like various things like this, limiting trans fats, like having more sugar, having more alcohol. So all these things seem to be associated with things that are then associated with heart disease. So this has been kind of well known, but again, like for a lot of these, causal relationship hasn't truly been established yet. And as you guys mentioned, in order to truly establish this, you need to do a randomized control experiment. That's pretty much the only way we could actually establish causation here. And so, sorry, my slides are like freezing. There we go. So there was some researchers who came up with this hypothesis that there is some impact of diet on heart disease, and they came up with actually a really specific hypothesis. So they said that replacing saturated fat with unsaturated fat basically reduces the risk of heart disease. So that means like if you consume like a lot of butter, like replace that with vegetable-based oils like olive oil or avocado oil. And that replacement should reduce your risk of heart disease. So this is at least what was some scientists' hypothesis. And then the explanation for why they thought this might be the case was just because this replacement reduces a particular kind of cholesterol, and we know that that particular kind of cholesterol is associated with heart disease. So that was kind of the scientists' reasoning for why this might be the case. This isn't a proof of it, obviously, but it's just kind of their reasoning for how they came up with the hypothesis. And then to show that this is actually true, they need to actually go out and do a randomized control experiment, and then make some conclusions based on the data. So that's kind of like what they'd have to do. And there actually was a study that in like 2017 said that clinical trials showed that using unsaturated fat to replace saturated fat actually reduces the incidence of cardiovascular disease. So that's just something they just like said. And so the idea is, if you wanted to actually validate this or test whether this is true, right? You guys mentioned you'd have to do a randomized control experiment. That's how we would actually have to do this. And so if you're designing an experiment and we wanted to assess this hypothesis, right? Like, how would we actually design this experiment? What are some of the things that we would have to do in order to actually do a randomized control experiment? Like, what are some of the steps involved in that process? Like, right from the beginning, like, I'm going to go out and do an experiment. What are some of the things I have to do? So someone's saying assign a treatment and control, but before I even do that, yes, get a sample first. So go and get people, right? So you have to kind of randomly sample some people. And then once you've sampled some people, then what would you do? So now I have like a sample of people that I want to study. Yeah, so separate into maybe randomized groups and then assign, to different groups. And at that point, then what would you do? So you've set them apart into groups. Now what has to happen? So I have these like sets of people, they're in random groups. What needs to happen now? At least in the context of the experiment. Like, how does the experiment proceed? I guess is more of my question. Yeah, so give somebody a specific diet, right? So maybe give the treatment like an unsaturated diet, and then give the control a saturated diet. So basically, you have to go out to some set of people and be like, all right, you guys are going to just eat like butter and ice cream for the rest of your life. And then go to some other people and say, you're just never going to eat ice cream again. And we'll just observe this. We'll observe what happens at the end of your life. And then that's what it is. And we'll look at the data. So that seems pretty hard to do. That's like it's not just like taking a pill and like they can't even tell the difference between the pill. Like you're literally changing their lifestyle. So it's very hard to do in practice. Yeah, someone's asking like, is this even ethical? So yeah, I mean, it's a tough thing to do. And as someone just mentioned, like, I'm sure a lot of people are just going to want to eat ice cream forever because like that's just what they're going to want to be, and they're going to want to be in that group. So you have to be a little bit careful about how you would do this. And it is really hard, but actually someone did do it. So there was a study, it's called the Minnesota Coronary Experiment. And so they actually did this, they achieved this. And this is actually considered one of the best designed studies or experiments like in the history of health. So it's really, really cool. And there's a few things they did to kind of make this a little bit more ethical and, but also kind of be very meticulous about it. So firstly, this was a double-blind randomized control experiment. So it means that like the patients don't know whether they're in the treatment or control, and even the people like administering the study don't know who's in the treatment or control. And it seems really hard to do that. Like, how would you do that? Because like we talked about how you're gonna have to somehow now potentially switch your diet to unsaturated food without telling the difference. Like, you can't even know that you're in that group, because if you knew that, maybe that would affect like your behavior and like other things that you do in your life, like exercise or whatever, right? So you don't want to affect like anything else in your life. You want that to be the only difference. So it is challenging how to do that. I mean, you need the food to like look the same and like taste the same, basically. But you know, they found ways to do this, and it's an interesting fact about this study was done in Minnesota, and at the time, the law basically said that like you had to distinguish like butter and margarine. Like if you were selling it in stores, like butter had to be in rectangular storage packets, and then margarine had to be in triangular storage. So it's kind of strange, but that's just that was what the law was, and they actually had the law changed for this study. So it's pretty crazy, and they talked about that in the podcast. But anyway, so it's kind of interesting. So they really did a lot of work to try to make it so that basically the treatment and the control wouldn't really know like the difference. Like they both think that they're whichever group, like is almost the same. And so they somehow found a way to kind of just maybe cook the food or whatever it is in a certain way that you couldn't really tell a difference. And in this case, the treatment group was the one that got the less saturated fats. So you got more like vegetable oil, less butter, things like that. And so they did this with over 9,000 patients, so really large sample size, and it was over 3 to 5 years. So they didn't have them like change their diet for the entire life. It was just for 3 to 5 years, and they kind of observed what happened after that. And so that's kind of how they designed the study. And so, you know, now it seems like they have kind of a very clear-cut way now to determine, you know, the result here. So you have 9,000 patients, you observe them for 3 to 5 years, you've put them into 2 different groups. One's having one diet, one's having another diet. And then from that point on, you get your data and you can make your conclusion. So it should be pretty straightforward, right? But it turns out the study was actually inconclusive, and they were actually unable to come up with a causal conclusion. So this is like this study was done in 1973. So this is like a long time ago. And so that's kind of interesting. So they weren't really able to come up with an actual conclusion for this. And so it just kind of, the study kind of fizzled out, and like no one really like went back to it or anything for a long time. But then in 2011, there's a researcher named Christopher Ramsden at the NIH. And so he wanted to study this problem again because he felt like there should be some kind of a link there, or some kind of a causation actually between like that particular part of diet and especially unsaturated fats and heart disease. And so he went in 2011, this is like almost 4 years later at this point. And he wanted to go back and see if he could get that data again and do the analysis. He wasn't quite able to do that. So what he did find was a master's thesis, which had some simplified data. So it was like summarized data. And that's actually the data we're gonna use today to analyze this study. And that was kind of the best he could find at the time. So this is a master's thesis done in 1981. So like maybe like 8 years after the original study was done. So, he got that data and that was great, but he really wanted to see there's a way to get the raw data somehow, because the raw data would be like really helpful to be able to have as well. So he actually went and found this guy named Robert Frantz, who is a professor at Mayo Clinic, a physician at Mayo Clinic. And this guy, Robert Frantz, is actually the son of the original kind of scientist who worked on the project in 1973. So he kind of went to Robert, and then his dad had already passed away at this point, but he said, like, do you have the raw data somewhere? So Robert like drove back to his family's house in Minnesota, And then like somewhere in the corner of the basement, they actually found all the raw like original data with like autopsies and like everything, like how these patients ended up dying and whatever it is about their entire life. So it's pretty crazy. So they went and kind of like dug up all the original data. And they were actually able to find everything, and it was finally like actually published and like shown to the world. But the idea for today, at least, what we're going to do is we're just going to look at the simplified data, the summarized data, and try to see if we can make some conclusions about it, and go about kind of how would we actually analyze the study, like, and I guess test the hypothesis. Really, is what we want to do. But before we kind of get to that, the data ended up showing that there was no difference in mortality, basically, between people who were in the treatment or control. So like it didn't actually seem to matter whether you took unsaturated, whether you had unsaturated fats in your diet or not. The mortality rates were like basically the same between both of the groups. And that's kind of what the result of the data shows, but they never really like published it. And so a question for you guys is, the fact the data didn't show any difference in mortality, like should they have published this information and published it in like a medical journal or something like that? What do you guys think? I want to hear from a few more people. Okay, most people are saying yes. Potentially. Yeah, someone said it's still useful to know. So like you didn't prove the like hypothesis that you claimed, which is that like unsaturated fats should lead to like lower heart disease. You basically showed that it didn't, but that's still information. I think that's still useful information for the world to know. And so it is something you should still publish. Just because your data and your study wasn't consistent with the alternative doesn't mean that you shouldn't publish the study. Like it's still useful. It's still useful information, especially with like this kind of a sample size of 9,000. It's a lot of people. There's maybe some bias there in why it wasn't studied, why it wasn't published. But the basic idea is, you should still publish it regardless of the result, even if it kind of disagrees with what you believe. So we'll actually kind of go through now through the data and think about how can we actually analyze this, and think about, what would our conclusion be if we actually looked at the data. So eventually what happened was, after they rediscovered the data, there's this like article in Scientific American basically says like the records were found in the dusty basement, and it basically undermines like decades of dietary advice. Because like in this entire time, like everybody's been saying like, oh, you should be having this kind of food because it's going to make you healthier or whatever. And so basically this data kind of conflicts with a lot of that advice. And it's just kind of interesting. Maybe if this had been published like 40 years ago, people wouldn't have gone on to like make such claims or whatever it is, or at least those claims could have been like potentially disproven. So it's just kind of interesting to see kind of the effects of that. So let's actually take a look at the data, and this is kind of how the data looks like in summarized format. So we'll actually go into the notebook now and take a look at it. So here's our actual data set. And so this is summarized. So we don't have like the raw data. If you had the raw data, you'd have like every single patient who was in the study. So we don't quite have that. We have the data that's summarized. And so here it's like summarized into buckets of ages. So we have, for example, people who are age 0 to 34, then people age 35 to 44, and so on. And then we also had this column conditions that just tells you like, were they on a particular diet or were on the control group. So here, again, the control group is like just eating normal like saturated fats. And then the diet group is folks who are eating unsaturated fats. So we have, looks like 5 age groups here. And then, so we have 5 age groups that took the diet, 5 age groups who took the control. And then you can see kind of the total number of people in each age group. And then you can see kind of how many ended up kind of dying at the end of the study. So as you might expect, like the older, people from the older age group more likely to die at the end of the study because they're just older. And then there's this other column here that we're not really going to pay attention to, but it's just like specific deaths of a specific way. But we're mainly just going to be focusing on like how many died, because we're just trying to see like what's the difference in the mortality rates of the people who like did the diet and did not. And so in order to do an actual like hypothesis test on this, we need to be able to get all that original data of like every individual person. And so we don't have that. We have this summary, but we can sort of hack it and create our own table which has all those people. Because for example, I know here that there's 1,367 people aged 0 to 34 who took the diet. And we know that 3 of them died. So from this information, I could basically create a table. I should be able to create a table that has 1367 rows where they're age 0 to 34, and then 3 of those rows should be people who died. So I should be able to simulate or kind of create a table with like a bunch of rows for each individual from this information. So that's what this next set of code does. So I won't really go through all the logic of it just for the sake of time, but that's essentially what this does. So here we can see we've taken that table. Now we have way more rows here. So we have like about over 9,000 rows, because remember this study had 9,000 people. And now we have each person is one row. So we've kind of reconstructed this using the summarized information. So this isn't the raw data, but we're just trying to like approximate it basically. And so we know that we have, 1,367 rows of people who are 0 to 34. So that's like all these rows that we're seeing right now. And then we know that 3 of them ended up dying. So we can see that right here. So these first 3 are the ones that died, and then the rest did not. So now we've basically kind of found a way to create this table that has individuals in the study all as like different rows in the table. And then, yeah, I wouldn't worry too much about the participated column right now, actually. But main thing to pay attention to is like, what was their age group, I guess? That's the best information we're gonna have, at least for right now. What's their conditions? Like, were they on the diet or were they just in the control group? And then did they end up dying or not at the end of the study? So these are kind of the only 3 things that we're gonna be worrying about right here. And so one thing we can do is if we use group on this table with just 2 columns or two names of the columns, we can see this data in a little bit different way. So this is actually the same exact summarized data that we saw up above, but now it's just grouped a little bit differently. So now we can see the age groups like right next to each other. So it's actually the exact same data as like the original table, but just kind of shuffled around a little bit. And this is really cool because now we can see the number of people in each one really easily. And so it's kind of cool. You can see there's like, in the control group for people who are 0 to 34, there's like 1,337, and there's 1,367 who were in that same age group but took the diet. So it's like almost 50-50, it seems like. So it's kind of interesting. So you can see like the way that they were randomizing the study, probably they're just like pretty much just like flipping a coin to decide like who is in which group. So that's kind of interesting there. And then finally here we can see the number that died at the end of the study. So in the 0 to 34, like 7 people died from the control group, 3 died from the diet group, and so on. And so what's interesting here is if you look at the 65 plus group, right, the control group had 162 people who died, and then the diet group had 190 people. So actually the number of people who died was more in the diet group, which is kind of interesting. So it almost seems like maybe the diet's actually worse for you. So like having unsaturated fats is like worse for you. Like that's kind of strange, right? So this is part of the reason also why this study wasn't published, because they weren't really sure how to interpret these results. Like that's really strange. Like we were thinking that unsaturated fats was going to help and like reduce the chance of disease and like reduce the mortality rate, but it looks like actually increase the mortality rate. So when you see this kind of a difference, like what's one question that comes to your mind when you see this in the data? Confounding variables? Well, yeah, potentially. There we go. Someone says random chance. So that was kind of the answer I was looking for. So, is it, yeah, someone else just said, is the difference due to chance, right? So yes, we did see more people who died who took the diet, but again, maybe this is just due to chance. Like it could have just happened. And then confounding factors technically is also the right answer too, because like maybe they died for other reasons. And that, that's basically what you mean. When you say like this difference is due to chance, basically means it could be due to like other reasons besides just diet and control. So it is possible the difference is due to diet and control, but it's also possible due to a million other things. So basically we'll just say it could be due to chance as well. And so the basic idea here is, we see this difference. It seems pretty large. I mean, 190 over 160, like it's pretty large, I would say. It's like almost, I don't know, 15% or something like that, 20% of the difference here. but is that like significant? Is that just due to chance? So if we wanted to assess whether there's a difference between kind of the proportion of people who died within these two groups is like due to chance or not, you know, how could we do that? Like if we had to answer that question, well, first of all, if we were designing an experiment here and doing a hypothesis test, what would the null hypothesis be in this case? What do you guys think? So we're trying to understand whether the difference between the diets is due to chance. Yeah, there's no difference between the diets. That's a good way to say it. So basically, like, it didn't matter which group you were in. Like, whether you're in diet or control, your chance of dying was the same. So it doesn't actually matter which group you're in. And then what's one thing we could do for the alternative? Yeah, I mean, one alternative could be diet is like lower chance of dying. In this case, the diet actually was like a higher chance of dying. So maybe it could be either way. So yeah, maybe to be safe, let's just say the alternative is going to be there is a difference. So we're not going to say about any particular direction. We're just going to say there's some difference between these two groups. So that's going to be two hypotheses. So again, null hypothesis is that it doesn't matter which group you're in. The chance of dying is the same, whether you take the diet or you don't. And then the alternative is going to be there is a difference. There's a difference in mortality rate. We're not going to say specifically which direction. Like maybe control is more than diet, maybe diet's more than control, but there is some difference in the mortality rates between the two groups. All right. So those are going to be kind of the two hypotheses that we're going to have. And so how would we test this? How are we going to go about testing such a hypothesis? So we're trying to test difference between two proportions. And we're saying like it doesn't matter which group they're in. So what's kind of, how are we specifically going to go about this test? Yeah, A/B testing. So you have two groups, and you're trying to see the proportion of, you know, what happens in each group, and you're trying to compare those things. So this is a situation where we would use A/B testing here. And then lastly, you know, if we're doing A/B testing, and then we said that the alternative is, you know, it does matter which group you're in, there is a difference. So in that case, are we going to be using absolute value here or not in our test statistic? Any thoughts? So we said that we're trying to test, null hypothesis is that, that there's no difference between these two groups, and then alternative hypothesis is that there is a difference between the two groups in terms of mortality rates. So would you use a absolute value or not in your test statistic? Yeah, you would. And so how did you know that? You looked at the alternative. So the alternative tells you whether you're going to use a absolute value or not. In this case, the alternative isn't saying that like one group is like larger than the other or anything like that. It's just saying the two groups are different. So when you say that they're different, that means we just care about the absolute difference. We don't care the difference is like super positive or super negative. Just care about absolute difference. Cool. So that's basically what we're going to do here. So we're basically going to find like the mortality rate of the people who are in the control, mortality rate of the people who are in the diet, subtract the two, takes the absolute value. That's our test statistics. Absolute difference between the two groups. So you can go through here and just look at kind of our overall data. So we're going to do this, first of all, for like all of the data, all of the people, all the patients. So you have control, you have diet. And so there's about 4,700 people in the control group, about 4,700 people in the diet group. And then you have 222 who died amongst the control, and you have 245 who died amongst the diet. So again, this is about maybe 10% larger than the 222. So it seems to be some difference here. But again, going back to what we saw earlier, is the difference real? Is it just due to chance? So first of all, let's kind of think about how we could calculate our test statistic here. So we're going to create a couple functions here to help us with this. So first, this function hazard rate is going to give us the proportion of people that died. So if we have all of our subjects and we can put them into like a format like this with counts, let's remove age. So if we can put all of our data and summarize it using group like this, then we can really easily see our data. We have, you know, control, there's this many people, this is how many that died. Diet, this is how many people that were there, this is how many that died. So if we have this information now, then we can basically calculate the proportion that died really easily. So if we have counts, which is just going to be a row, let's say, it's just going to be a row of this table. So let's assume that's what counts is. So if counts is a row of this table, then we can basically just take that table and then take the number that died and then divide by the number that participated. So for example, if I passed in this row, it would just take 222 divided by 4738. So that's how we can find the proportion that died within a particular row. And then now that I have that function, then I can create a function here that's going to tell me the difference in the two rates, the two hazard rates, amongst everybody in my table. So this is going to be the table here is going to be expecting like the entire table of all the individuals. Because again, for an A/B test, like we need to have all the individuals. We can't just like separate them out into like categories of just like different groups. We want to have all the individual people. So if you have all the individual people, we're going to basically run this line here is the same thing as the cell up here. So basically, we're just going to group everything into this table. Now we have the counts in these two rows here. And then finally, we can just pass in each row individually into this function hazard rate. So first calculate the hazard rate of like row 1, subtract the hazard rate of row 0. So this is arbitrary. You could have done either order. You could do 0 and then 1, doesn't matter. And once you have the hazard rates of each hazard rate is the same thing as just proportion that died. Then we just take the absolute value of the difference between the proportions. So that's all we're doing there. And so if we can run this function here and we run rate difference on our subjects table, we get that there's a difference of 0.005. So the proportions are different by like 0.5%, looks like, in absolute value. So that's kind of how we get our observed test statistic. So this is going to be our observed test statistic. So any questions so far about this? Oh, someone said, in this case here, could you have used column instead of item? So we need to use item here because we're trying to get a specific number, like a specific single number. If you do column, that's going to return an array, and that's not exactly what we want here. So we want a specific item within the column, or within this row rather. And this row is already kind of, yeah, this will basically just grab like what's the item at this column for this particular row. So this gets us the individual number that we want, and that allows us to divide by 2. And then what does row 1 do? So row 1 says get the row at index 1. So index 1 is actually the second row. And then over here we have row 0. So that's the row at index 0. So index 0 equals the first row. So this is basically just saying take the second row, calculate its hazard rate, and then subtract the hazard rate of the first row. But the order here doesn't matter. So you could have done either way. And then what is counts? Counts is basically just this table here. So we took this code, drop age, and then group on condition, and then sum up the values. So I just took that code and put it back down here. So we're just basically saying, take your table that you have of all of your individuals and then summarize them into these just like 2 rows of data. And then once you have the 2 rows of data in counts, then you can calculate the rates really easily. So that's basically what we're doing there. And so now we have a way to do this. I'm going to skip those couple lines. We'll go back to those later. So now that we know how to calculate the difference in the mortality rates between these 2 groups from all of our individuals, right? The last step is now we're going to have to do our A/B test. So when we're doing an A/B test, how exactly would we perform the A/B test? Like we have this table of all our individuals. We know like treatment or control, and then we know like whether they died or not. So those are kind of the things that we know about them. So what do we need to do now to do the A/B test? Yeah, so we have to shuffle. So we have to shuffle our data, and specifically, what are we going to shuffle? Which column are we going to shuffle in our table? Let me show you the original data to give you a hint. So these are the 4 columns that we have here, and I guess we're going to ignore participated. So condition, there you go. So we're going to shuffle conditions. We want to keep everything else the same. You know, we want to keep their age the same. Whether they died or not, that's like a result. We want to keep that the same. The thing we want to change is the shuffle. Because remember, we said that the null hypothesis states that it doesn't matter whether you were in the diet or the control. your chance of dying is the same. So if it doesn't matter, that means you should be able to just shuffle that condition column. That's what we're going to do. We're going to shuffle the condition column. So this is kind of how I'll write it out. So we're just going to create this function called test. And so I'll break it down into steps here. So the first step, what we're going to do is calculate our observed test statistic. So this is the same thing that we just calculated up here, rate difference on subjects. So just calculate the rate difference in mortality for your table that we actually have, like the actual data. So this is the observed test statistic. And then we'll do shuffling 200 times. So we're going to have 200 kind of simulations of what could happen if we shuffled that condition column. And so this is what we're going to do here. And then we're going to store kind of the rate difference within each shuffled table in an array called stats. So we're going to have like 200 different rate differences essentially from our 200 simulations. So now we have our for loop. And then here's what the for loop does. You can zoom out a little bit. I don't know if that really helped. But our first step here is take your table, and then we're going to select died, because that's really just all we care about is how many died basically. And then we're going to sample this with replacement, and then take the died column from it. Well, I guess here we're sampling just died. I guess you can do it either way. It doesn't actually matter. In this case, they chose to do died, to sample died. But you actually get the same result. Yeah, I don't know, actually, this was written a little bit differently. But you could have done it with condition, you could have done it with died. It actually doesn't matter. I think it's a little bit, this code is a little bit easier with died. But basically, they actually shuffled the died column, and then they basically created the original table with a new column of like the died, the shuffled version of died, and then calculated the rate difference between the people who, like between diet and control, the number of people who died. And then once they had the rate difference, then they append it. So there's some confusion here, so let me go back up to the table here. So you could shuffle condition, which is just like died and control. You could also shuffle died and just keep the condition the same, and then that's going to be true and false shuffling around. It's actually equivalent, because if you think about it, in order to calculate like the rate difference, all we really need to know is like the died column and the condition column. We don't need to know the age column, and we don't need to know the participated column. These are the only two columns that matter actually. And so if you just have two columns that matter, then like shuffling one is equivalent to just shuffling the other one in that case. So you could shuffle either actually, but this is a very specific case. If you had like 6 columns that you cared about for some reason, then you'd only want to shuffle the one that you do. I think in this case, it's just like a little bit easier because the math is just like a little bit simpler here. So anyway, so this is kind of how we can do that. And so now we have kind of a rate difference of our simulated outcome. And then finally, we can kind of append it to our array that's storing like the outcome of every single simulation. Once we have all of the simulated outcomes of what could happen if we shuffled things, then we can finally calculate the p-value. So we just do np.count non-zero and just count how many of the stats are greater than or equal to the observed, and divide by the number of repetitions, so divide by the number of simulations that we did. So basically p is going to be what proportion of our simulations resulted in a difference in mortality that's greater than or equal to the observed difference that we saw. And again, these are absolute differences. So that's why we keep looking at greater than or equal to, because it can just be anything that's like larger is like evidence against the norm. So we can actually run this. So it takes some time to do like all the different simulations, and it'll basically return the p-value for us. And so we already know what the result is going to be here based on what I told you, but you can actually just see like what it's actually going to be. This is a little bit slower than I was expecting. Okay, there we go. So we observed an absolute difference of 0.005. And then the question was, okay, we observed some difference in mortality between treatment and control. We actually saw that treatment resulted in a higher mortality rate slightly. But the question was that just due to chance, or is there a real difference there? And so we did our simulations, and it turns out of our simulated differences, only 27% of them were kind of beyond the observed value. So that proportion is still like quite large. 27% is actually quite large. And so if we wanted to like reject the null, we would have wanted to see that like, a lot of them are like above or actually, sorry, we would have wanted to see that like very few of them are above the absolute difference that we saw. Because if what we saw was like a real difference, then if you actually like simulated a bunch of values of the differences, most of the differences should have been like pretty close to zero. So most of the differences should have been a lot smaller. So basically like smaller values should have been more evidence for the alternative. In this case, like there were values even larger than what we saw. So what we saw is not that special, essentially. So that's what that's saying. What we saw is like kind of expected if they were the same. And so that's the idea there. And so again, why are we doing greater than or equal to? It's because we're looking at the absolute value here in this case. So we're looking at the absolute difference between the mortality rates between the two categories. And so we want to know kind of, if we simulated and under conditions where like it doesn't matter, how often would we get something like as extreme as this or more extreme? And if that probability is like really low, that means that what we saw is like actually really extreme. So that's kind of what we do greater than or equal to. In this case, the probability is like kind of high, 27%, that's a lot. It's a lot of the simulations that went above what we saw. So that means what we saw is not that extreme, which means that what we saw is like pretty consistent with the null, that there is no difference in the two groups. So failed to reject in this case. So that's kind of the conclusion. What is going on? Oh no. I think I clicked something I shouldn't have clicked. Okay, here we go. So this is kind of the conclusion, was basically you failed to reject the null. And so if you want to go back to the podcast, listen to it, it's pretty cool. There's this particular segment where Malcolm Gladwell actually interviews Robert Frantz. So that's the son of the person who did the study. And then he basically tells them like, I'm going to publish the results from your raw data. And like, it basically, disagrees with your dad's original hypothesis that like unsaturated fats leads to a healthier lifestyle or like lower mortality rate. And are you okay with that? And then Robert basically says, yeah, that's fine. Like my dad's a scientist, so that's what he would have wanted. So the idea is, you should still publish your results, even if they disagree with, what your hypothesis might have been. It's still valuable information for the world, even if you fail to reject the null. So it's just kind of a good lesson here. So I think we'll stop with that, and I'll stay on to answer any questions. But I think that's it for today.